I have a great honor to present Dr. Adashi today. And Dr. Adashi is an academic physician executive. He is the former Dean of Medicine and Biological Sciences at Brown University. He has many achievements and honors. He graduated from Tel Aviv University School of Medicine. He had a degree from Harvard Chan School of Public Health program. He is a former president of many uh, institutions, including SRE, SGI, and AGAS. He also served as an examiner and director of the Division of Reproductive Endocrinology at ABAC, and he is currently serving as a tenured professor with the Department of Medical Sciences of the Warren Alpert Medical School of Brown University. So I am now leaving the stage to Dr. Adashi. Thank you very much for joining us.
My distinct pleasure. And thank you very much for the kind introduction. Can you hear me all right?
Yes, we are able to hear.
Okay. Well, today we will speak about the future. As many of you know, in about 3 years, we will be recognizing and celebrating the 50th anniversary of IVF, which originated, of course, in the UK. This happens to be the Lancet report, authored by Doctors Steptoe and Edwards in 1978, reporting the birth of Louise Joy Brown, the very first IVF baby ever born. As you may also recall, Professor Edwards was the recipient of the Nobel Prize in 2010. The only reason his two all-important collaborators did not join him in terms of the award is because, sadly, both have passed away by then. And it is the policy of the Nobel Prize Committee to award the Nobel Prize only to living recipients. Dr. Edwards himself passed away in 2013, this being the Lancet obituary of the same. In the United States, as you well know, we were somewhat behind, but ultimately, courtesy of the Norfolk team, headed by Howard and Georgiana Jones, on December 28, 1981, the first American IVF baby was born, that is Elizabeth Jordan Carr, who was the first American IVF baby whose birth was recognized on virtually every outlet, from the Boston Globe to Life magazine. But today we will be speaking about, if you will, the successor of IVF, or at the very least, the modifier of IVF as we go forward. Specifically, we will be discussing in vitro gametogenesis, the beginning of which has everything to do with the contribution of these two leading Japanese investigators. The first is Mitinori Saito, MD, PhD from Kyoto University, and the second is Katsuhiko Hayashi from Kyushu University. However, when I first met these two gentlemen, which was around 2013 or thereabouts, in Japan, they worked together in Kyoto. And I had the distinct pleasure of visiting with both of them and spending the morning discussing what was then an evolving project, but one with a clearly bright future. As is true of every novel concept, the progression that one follows is studies in the rodent, which lead the way, and only later, gradually and carefully, transitioning to the human. And that's roughly where we are today. None of this would have been possible without the, I don't want to say invention, but the introduction of pluripotent stem cells, which come in two varieties, embryonic or induced. And I'll say more about that, of course. In theory, however, pluripotent stem cells can replace virtually any cell type in our bodies. For example, in individuals who lack amacrine neurons in the retina, in principle, we could replace those with lab-designed counterparts. The same holds true for the dopaminergic neurons that seem to be underperforming in Parkinson's disease in the striatum. And in principle, we could replace those with in vitro-derived dopaminergic neurons. And the same holds true for motor neurons, which, if interrupted, for example, in the spinal cord, give rise to paralysis. To illustrate the potential of pluripotent stem cells, I will use the last example, which provides you with a truly stunning illustration of the power of stem cells and what will doubtlessly be referred to as stem cell medicine. I'm making reference to a very recent report in Nature magazine, which described the application of stem cells to the spinal cord of a paralyzed individual or paralyzed individuals, one of whom was fully cured, if you will, and was able to walk. That, I think, is perhaps the most striking illustration of the potential of stem cells and what they can produce. Of course, we will not be focusing today on neurologic complications, but rather we will discuss the applications in the context of reproductive medicine. And specifically, we will discuss the novel phenomenon whereby gametes need not be necessarily derived by surgical means or otherwise from a man or a woman. Rather, they can be derived from a skin cell, for example, and by dint of the conversion of that skin cell to a stem cell, one could then redirect the development of that stem cell to a gamete. Science magazine appreciated the revolution that is underway and dedicated a spread to in vitro gametogenesis back in 2021, authored by Professor Saito and Hayashi. The New England Journal of Medicine, not to be outdone, published its own paper on oocytes from stem cells, commissioned from Mary Herbert and Azim Surani, both from the UK. More recently, in 2023, I had the privilege of organizing and chairing a 2.5-day workshop of the National Academy of Medicine in Washington, D.C., which was dedicated solely to in vitro gametogenesis. You might also find it of interest that the Nuffield Council on Bioethics, which is the premier bioethical institute of the UK, when it defines its agenda in the human reproduction arena, the first item that tops the list is in vitro derived gametes. Yes, they are planning to discuss this topic and others. But at the top of the list, in vitro gametogenesis appears to be leading the pack. We probably will not have any difficulties in agreeing that in vitro gametogenesis is a disruptive technology. Whether or not it's achievable in the human, I would say still leaves some room for doubt, although the optimistic view is that it will happen, of course, along a timeline that remains to be determined. To be sure, we're not quite there yet, but we can see it coming. All of this, as I already indicated, is contingent on the availability of pluripotent stem cells, which can go anywhere, including towards gametes. There are two ways to derive so-called pluripotent stem cells. One is known as the somatic cell nuclear transfer, or SCNT for short, which was developed in 1958 by John Garden, then at Cambridge University in the UK. He started with a somatic nucleus that he transferred to an enucleated oocyte, which gave rise essentially to a zygote, which developed into a blastocyst, gave rise to an inner cell mass, etc., from which he harvested so-called embryonic stem cells. In 2006, Professor Shinya Yamanaka from Kyoto University proceeded to develop the second technology to produce induced pluripotent stem cells, starting with the somatic cell, say a skin cell, transfecting it with select transcription factors, and producing what we now know as induced pluripotent stem cells, which is really the main workhorse right now for the generation of differentiated cell types, whatever they may be, including gametes. Both individuals were honored by the Nobel Prize in Physiology and Medicine back in 2012. But to go back to our subject matter, in vitro gametogenesis is about harvesting a somatic cell of one kind or another, converting it by one of these technologies, most likely the more recent technology, to induce pluripotent stem cell, and then guiding that induced pluripotent stem cell towards a gametogenic fate. Now that may be easier said than done. You have to know what the prerequisites are. And specifically, you need to know the cues you need to apply to the stem cell in question, the sequence by which you will apply those cues, the timing thereof, and you might have to take into account, in this case, the niche in which these cells are enclosed. By that I mean, oocytes are obviously surrounded by granulosa and theca cells. And by the same token, sperm are surrounded by Sertoli cells. Those are the niche cells that provide important information to the gametes. And so you need to take that facet of this cell type into account. The beginning, as you can imagine, was modest. But back in 2003, Hans Schroeder reported on the pages of Science the derivation of oocytes from mouse embryonic stem cells. At the time, Dr. Schiller was a postdoc at the University of Pennsylvania. Since that time, he became the director of the Max Planck Institute for Molecular Biomedicine in Germany. That same year, Toshiaki Noche from Japan reported comparable efforts on the pages of the Proceedings of the National Academy of Science. A year later, George Daly on the pages of Nature, Dr. Daly being the current dean of Harvard Medical School, reported on the derivation of embryonic germ cells and male gametes from embryonic stem cells. And René Rehopera, who at the time was at UCSF, reported the spontaneous differentiation of germ cells from human embryonic stem cells in vitro. As we sat and watched the evolution of this field, significant papers took place prior to 2010 on some of the most prestigious journals. In the subsequent decade, between 2010 and 2020, more of the less transpired, this time in the human, on the pages of Nature, Cell, etc. And so when we summarize the state of the art in 2015, we can say that the germ cell specification pathway is not conserved between the rodent and the human. In other words, one would have to figure out the human separately. The rodent was not going to provide the exact roadmap. And we also realized that the genetic networks involved are quite distinct as well. And so, as you obviously can imagine, a human is not a rat or a mouse, and very different forces have to be taken into account. But what we did know is that induced pluripotent stem cells can be converted to primordial germ cell-like cells. What we couldn't really accomplish at that point in time was the conversion of the latter to mature haploid post-meiotic gametes. In a word, we mastered the extragonadal component, but we failed to master the intragonadal counterpart. And so the final frontier, which was yet to be conquered, was in vitro gametogenesis all the way. This was first accomplished by Katsuhiko Hayashi in a Nature paper using the rodent system in 2016, about the time when all of us were at the annual ASRM meeting in Salt Lake City. He started the process with induced pluripotent stem cells, combined them with gonadosomatic cells, produced primary oocytes, eventually M2 oocytes, fertilized those, produced blastocysts, and gave rise to pups. And so for the first time, at least in the rodent, one was in a position to reconstitute the entire cycle of the mouse female germline. His counterpart, Professor Mitinori Saito accomplished the same in the rodent male. But that still left us with the human paradigm, which is, after all, what matters in clinical medicine. All we can say today is that in 2018, Professor Saito, on the pages of Science, reported the utility of human primordial germ cell-like cells, which were combined with xenogenic ovarian somatic cells. And using his technology, he was able to guide those primordial germ cells to the oogonial stage. But that's, of course, not the M2 stage, which is where we would like to be. And so as you speak today, there's still room for improvement or room for science to take us to a point where in vitro gametogenesis be functional and useful in the human. In a word, this is still something we can look forward to, but it is in the future rather than in the immediate present. Assuming we get there, the scientific and translational promise will be substantial. On the obvious side, we will, for once, have an inexhaustible supply of germ cells. And for the scientists who care to study those germ cells, they could now carry out so-called functional non-mutant analysis to their heart's delight. In other words, they could knock out one gene at a time and ask, what does it do? We could also, for the first time, do meaningful germ somatic cell interaction studies in the human by having both cell types in a dish under our control. More importantly, however, on the clinical side, we may finally be in a position to reverse germ cell failure for whatever reason. Simply by dint, I say simply, but ultimately by dint of autologous gamete replacement, potentially gene-edited gamete replacement. For example, what if you're starting off with a patient with a Turner syndrome? You'd need to do some fixing before you move on. And for the first time in human history, since we all got used to the notion of Adam and Eve, we may well end up, and there's every indication we will, with same-sex genetic parenthood. Up until now, of course, same-sex parenthood relied solely on the adoption of children. But early indications are, and some Nature papers attest to that, we are likely to be entering an era of same-sex genetic parenthood. In the case of two men, of course, they will need a female surrogate to carry the embryo. But in the case of two women, that will be taken care of within that parental unit. Now, when and if we have arrived at the production of IVG, its impact on IVF will be palpable. It will, in principle, eliminate the need in gonadotropic stimulation and in egg retrieval, which is to say it will substantially simplify the process. We also may no longer be dependent on gamete banks, which assist us in the cases of gamete donation. And all indications are that IVG will convert IVF to a laboratory procedure. We will still need to replace the embryo, of course. We'll have to prepare the endometrium, we'll have to transfer the embryo, but much of what transpires prior to that may well be done away with. In other words, we will require endometrial preparation and transfer, but not much more. In theory, this could improve the affordability of IVF, which is not always affordable, and thereby improve access. In other words, render IVF accessible to a larger segment of the population. I put a question mark at the end of that only because we have all observed many examples of circumstances wherein affordability was predicted but not realized. Something about the American psyche sees to it that the prices are ultimately jacked up. None of this, of course, can or should proceed without rigorous regulation. And when I say rigorous regulation, I mean FDA regulation or FDA jurisdiction. At the FDA, IVG, if it will come to that, will come under the watchful eye of so-called CBER, or the Center for Biologics Evaluation and Research, which will categorize IVG under the category of what they refer to as HCT/Ps, or human cells, tissues, and products. Now, some of you may wonder by now why we are making reference to scientific work that largely, if not exclusively, originated in Japan. Why aren't we conducting US-based research funded by the NIH? Although the answer may not be completely clear, many investigators have taken note of the so-called Dickey-Wicker Amendment, which was passed in 1996, which prohibits the NIH from supporting embryo research. And it's entirely possible that grant applications for IVG, which ultimately, of course, are all about embryo research, may simply not be funded because the NIH is precluded from doing so. And so it is entirely possible that American investigators have recognized this reality and have avoided applying, if you will, knowing full well that they may not be funded. Nevertheless, once the FDA approves IVG, however it is coming to fruition, we will have at our disposal gametes to order, if you will. Also, at this time as we speak, it's important to note that the commercial sector has discovered IVG and has swung in and is planning to conduct at this point phase 3 clinical trial. The company in question, Gamito, is New York-based. The product is known as Fertilol. We don't know much about it, but we do know that the FDA did approve recently phase 3 clinical trials using this technology, which is to say that, at least in the commercial sector, which does not share with us all the insights we would like to have, IVG may be proceeding and ultimately may enter the commercial sector. This is just another indication that the commercial sector is entering this field, and it's just a question of time before this will become a reality. Another company, by the way, is also entering the fray, and so you now have two commercial companies working towards an approval of a product that will be essentially the realization of IVG. So, as we often have to say in this business, stay tuned, because we're not quite there yet. But the promise is real, and it's just a question of time. And so it's important that we all are apprised of what's coming down the line, which is the purpose of this presentation. I thank you very much again for the privilege of sharing these insights with you. Undoubtedly, UCSF will be amongst the leaders when and if this technology becomes applicable. So stay tuned. Thank you very much.
Thank you very much, Dr. Adashi. So now we can go to Q&A. Any from the audience, any questions that anyone would like to share, first of all? And I'm also looking at the chat. So, Dr. Adashi, I have one quick question. Thank you very much for this nice talk. Uh, let's say this technology approved tomorrow. And what do you think about the biggest issues that we will be coming across? Is it mostly a biologic problem, like we will see some if unexpected impacts or effects on the offspring, or do you think that it is going to be mostly a problem in the how we use this technology? What are your thoughts?
Well, I retain strong confidence in our regulatory mechanisms and in our scientific prowess. And so I don't think we need to fear this technology or worry about adverse outcomes, although we should always be alert to that possibility. But on the assumption that it proceeds under the guidance of the FDA, and when I say FDA, as you know, we're talking about an expert committee that is invariably convened by the FDA when such applications are being entertained. And so some of the best people in the nation will be sitting in a room and will be assessing the product that is being offered, presumably by one of those two companies I mentioned. So no, I remain very confident in the system we have in place. We all know many of the products that went that way and are being used safely by all of us day in and day out. And so as long as we cross our T's and dot our I's, I don't know that we need to be fearful or concerned about the outcome. Time will tell, but I would not start off by shall we say, emphasizing the fear factor. We need to be circumspect. We need to be careful. We need to subject this technology to all the possible oversights we can. But at the end of the day, this will have a salutary effect, in my view, on the therapy of infertility and will improve the lot of women worldwide.
So, Dr. Adashi, we have another question from the audience. The question is, could you comment if parental age will have the same implications for genetic birth defects with stem cell gametes? Meaning that because the aging may also have an impact on the somatic cells. So, can you comment on that?
Yes. While I don't have any first-hand evidence, I think common sense would indicate that the answer is affirmative. Um, there is a reason nature is having us start our families early. That's not to say that individuals who are beyond the reproductive age or for one reason or another have lost reproductive function should be precluded from starting a family. But nature clearly designed reproduction as an activity that is primarily undertaken by the young. And so, yes, I think I would be concerned about genetic abnormalities that accumulate over time. And the skin, for example, if it were the source of the gametes, is hardly immune from that. So yes, I think the younger the better. But that still is the leading mode of reproduction today. And I think it's less likely, of course, that reproduction will inspire later in life. But if it does, it will probably require additional caution and additional monitoring to be absolutely sure that the offspring are as well off as their younger counterparts.
So thank you very much. So any other questions from the audience? And we got a very similar question also about the age affecting on aneuploidy, but you already mentioned that to Dr. Thanks for the answer. So any other questions before we conclude this grand round? Okay. So thank you very, very much, Dr. Adashi, for joining us and
My distinct pleasure. My distinct pleasure. Thank you.
so have a wonderful day, everyone. Thanks a lot.
Thank you.